During the previous lectures, we have done regression analysis based on the assumption that all the classical linear regression model assumptions have been satisfied. However, starting from today's lecture, we will start relaxing those assumptions, and we will see how this relaxation of assumptions affect our estimation results. And the first consequence of violating one of these assumptions that we will discuss is called multicollinearity. So let's see what it is. From this slide, you can get a very quick overview of what we're going to do. So I will quickly explain what multicollinearity is. Then we will move to the part related to the consequences of this phenomenon. After this, I will show you how to detect multicollinearity. And in the very last section, I will show you how to deal with multicollinearity. So let's have a look what it is. So when we relax assumption number 8, there is no exact collinearity or linear relation between the x variables, we might get the problem of multicollinearity. So multicollinearity arises when there is some linear relationship between the x variables. This linear relationship can be either perfect or not that perfect. Let's start with the case of perfect linear relationship or perfect multicollinearity. So we say that there is a perfect linear relationship between the variables when the following condition is satisfied. When we have some independent variables from x1 all the way to the last independent variable, let it be xk. So when we assign some coefficients to them and when we sum them, we get that they're equal to 0. We can rearrange this equation to get, let's say, an equation for x2. So what we need to do is we need to move all the terms to the right side and then divide both sides by lambda 2. When we do this, we get the equation that allows us to estimate x2. We can do the same for x1 or xk, right? So we just move all the terms to the right with the exception of the variable in question and then divide both sides by the coefficient assigned to it. So from these two equations, you can see that x2, for example, is exactly linearly related to other variables, or in other words, this equation shows us how x2 can be derived from a linear combination of other x variables. So if we have the case of perfect multicollinearity, the regression coefficients of the x variables are indeterminate, so we cannot determine them, and their standard errors are infinite. Actually, I would say it in another way. So if we have perfect multicollinearity, the regression coefficients have infinite standard errors, and because of them, we cannot determine them. However, believe me, I don't think you will see perfect multicollinearity that much, but you will see a lot of less than perfect multicollinearity. So you will deal with variables that are kind of intercorrelated, but not perfectly. And this happens when we have the following. So if you compare this third equation with the first equation, you will see that the only thing that makes them different is the presence of the error term v. So in this case, when we rearrange the third equation and get an equation for x2, we will see that x2 is a function of the other independent variables, x1, x3, and all the way to xk, and in addition the error term. So therefore, from these two equations, we get that x2 is not an exact linear combination of other x's because it is also a function, it is also determined by the error term. And this is the case of less than perfect or non-perfect multicollinearity. So in this case, the regression coefficients can be estimated, they can be determined. However, they will still possess very large standard errors, which means that even though we can estimate the coefficients, they won't be that much precise and accurate. There are different sources of multicollinearity, and I have mentioned some of them on this slide. So first of all, the problem might arise when you start collecting the data. For example, if you take a very small sample or a very limited range of values, you might get the problem of multicollinearity. So when you will be doing research in the future, try to make your sample as diverse as possible, as big as possible. Another problem is model specification. Some lectures before we've discussed various functional forms, and using the incorrect functional form might lead to the problem of multicollinearity. Another source of multicollinearity has to deal with an overdetermined model. This is the case when you have too many explanatory variables, when you have too many independent variables. Please also try to avoid them. You might be very tempted at some point to include as many independent variables as possible, but believe me, most of the time it doesn't work out well. So it's better to have a limited number of explanatory variables, but make sure that those variables are really good and they really belong in your model. Another source of multicollinearity is the existence of so-called common trend. In other words, your independent variables might follow some common trend, which means that all of them at the same time increase and then all of them at the same time decrease over time. So this is the case of a common trend. So they follow the same pattern. Their behavior is exactly the same. They either increase over time or they just decrease over time. And this could be another source of multicollinearity.